So I think most of you have been able to proceed at least till more than 50% of what is there in the flow sheet. Many of you have completed till heat exchanger. So I'm happy that all of you, I mean, most of you could attempt it. So we'll pause here for some time, and I want to invite once again Naren sir, who will be giving us a talk on aspects of creating flow sheet towards process development. So participants, you can pause for some time, and I would like to hand over the stage to Naren sir. Over to you, sir.
Yeah, thank you, Priyam. I suppose I'm audible.
Yes, sir, you are.
Yeah. So, good afternoon to all. I hope everybody practiced the tutorials to a very good extent, and you have a fair idea of the different unit operations, or the tools, objects, as you call in needle-mism language. And I hope by the end of today, you also have a lot of tutorials to practice, and slowly you will get accustomed to it. I could see some of the comments that you are having some issues with using certain objects or how to specify those conditions. But I think you can post your queries in the spoken tutorial forum, and it will be answered. And as you practice, that's the first thing. And as you practice more, you will get more comfortable and you will be in a better position to do that. Now, what I have planned for today is something I would like to discuss and then write, and that's why you just see a blank sheet. It's not a well prepared PPT talk today. It's going to be an extempore. And I'm going to touch something on the aspects of flow sheeting. So it is on the aspects of flow sheeting towards process development that we started as a holistic idea. So let's see what is, if I say as process development, right? So let's say that I want to produce a chemical, right? Some chemical. Let's example that I want to produce ethyl benzene. Okay. Now you must be able to connect it. Eventually, this ethyl benzene is what gives you styrene, and styrene is what gives you polystyrene. And polystyrene has lots of utility products associated with it. So that means indeed ethyl benzene is a very useful chemical for all our purposes. Now let's say that I want to produce this in some capacity. Let's say I will say that I want to do this in 1,000 tons per day, right? This is all the information to begin with. Let's say that you need to produce ethyl benzene, and you need to produce at this much quantity per day, and you are asked to develop a process, right? So that means you are asked to develop the sequence of operations that you have to perform in such a way that you will get this product of this particular capacity, right? This is what a chemical engineer at an undergraduate level, this is one competency expected from a chemical engineer at an undergraduate level. And as an operational person, as work in industry, you are going to actually work on these operations or equipments which are already being put in place. Either you are going to operate this in a good manner, or you are going to enhance their efficiency of that particular plant based on your analysis. This is the context of today's talk for the next 20 minutes or so. So all I know is ethyl benzene. So how I'll begin this flow sheet? If you look into your tutorial problems, you are well defined. You have been given the temperature, pressure, the compound names and everything. But that will not be the case when you want to go to the next level. The only information is it is ethyl benzene, 1,000 tons per day. That's it. So the first thing what you need to know is probably that what makes this ethyl benzene. So that means the reaction that will give you ethyl benzene. This is fundamentally from chemistry, and you know that ethylene plus benzene, I'm just writing in a short form without writing the molecular formula of C2H4 and benzene ring, just to make sure that it's easier. especially for the second years also, and the first years. So it is ethylene plus benzene just gives ethyl benzene. That's it. Now the next question will be, so that means if I have these two reactants and if I make them react, I will get ethyl benzene. That's fairly straightforward. Now what is the next point then? That means how much ethylene and benzene is required to make 1,000 tons per day of ethyl benzene. So that means we need to answer this question, right? Now you might have studied this as part of your process calculation course, but just try to do it the other way around. Can we answer this question from using DWSIM? Not the manual method, not using the process calculation method. I'm just saying that using DWSIM, can you think of answering this question? Or if you are assuming that you have even found out the answer manually, if I ask the question the other way around, can you use DWSIM to find out whether your answer is correct or not? Do you think like it is possible in DWSIM to do this?
Yes.
Yeah. Right.
Yes, sir.
So that means it should be possible, because you can take a reactor, okay, right, send in ethylene and benzene, and then try to get ethyl benzene, right? Do you really worry about temperature here if you want to find answer to this question?
No.
No, right? So do you think is this amount going to vary depending on the temperature that you are going to take at this stage? At this stage, no, right? Because why? If you, yeah, I think somebody was putting on the chat, or I think I have a difficulty to see the chat when I'm sharing the screen. Okay, so I think when I'm sharing the screen, I have a difficulty to see the chat, but right? Okay. So the point is, this is answerable using DWSIM also. So what I mean to say here, I know emphasize here, is you can use DWSIM as your learning partner, right? So you can use the tool to better learn your concepts also. All you have to take is DWSIM, put a conversion reactor, and in this conversion reactor, you will choose 100%, and then you can find out how much ethylene and benzene is required. Now come to the third point. Now, is this conversion that you take as 100%, is this okay? Is this okay to use 100% conversion?
No, sir.
In a process?
No, sir.
Right? So that should be their next frame of thought, right? You need to know whether is this 100% is correct. Can I really have 100%? The other way of slightly connected question at this point is, we want to make 1,000 tons, let's say, of ethyl benzene. What would be the specification of that product? In a simplest sense, is that 100% pure?
No, it has some impurities, obviously.
It has some impurities. So if you just scan through the chemical manufacturers, they will specify, right? It is probably 99.9% ethyl benzene, and then it's okay, 0.06%, maybe something else, and like say 0.04%, something else, right? This A and B need not be just ethylene and benzene. These are some other species, and it can also be ethylene for that matter, right? So that means you either come to a point where you think out this conversion, or you certainly know that from another thought process that it is not going to be only ethyl benzene in the stream after the reactor. It is certainly going to have other species also, right? So is this comprehensible? So to all the participants, especially the second and third years. So that means my reactor, which I draw now in DWSIM, I cannot only think like ethyl benzene. I may have here only ethylene and benzene, but here I do expect that there will be some ethylene and some benzene as well. So this is my reactor, right? So this could be 99% and this could be like 0.6 or whatever, 0.4. This could be some numbers, any numbers at this moment. But the point is, this is no longer pure. That means we need here a number which is not 100, correct? You will not be able to choose 100 here, because if you choose 100 here, it will definitely come as a single component, right? And if it comes as a single component, in another way, there won't be any chemical engineers as such required in many process industries, because you are not going to have only any separating equipments after that, right? But then comes to the point, number could be, right? How to get some estimates of this number. Now this again can be used DWSIM to answer this. Now here we need to know some fundamentals of chemical engineering. I'm not going to go into very detail of that, but I will just put some flashy keywords. So my idea of this 10-20 minutes is to give a holistic view of how you can use DWSIM to learn your concepts and also at the same time apply your concepts to build a flow sheet that you want. Rather, so that means construct a digital process plant, as I said yesterday. One is the rate-based information that we have, and another is an equilibrium-based information. Both of these can give some idea of this realistic conversion. Remember, I have never put any choice of reactor here. I never said here it is a CSTR or a PFR or a bubble column or a packed bed, nothing. I have never even told here what is a catalyst required. We don't even require here any temperature. Conceptually, we are trying to find out what should be the temperature, what should be the pressure, everything. We are only at the nascent stage of the process, developing a process. This is something, is an information that we have to input only in simulators. For those of you who have studied in the third year and above of chemical engineering, you know that this is actually from CRE part, the chemical reaction engineering part, and the rate constant is an experimental parameter that we need to assign. And that is why in your tutorial statements, you have this rate constants given. Whereas this is something, it is computable. Okay, that means this can be estimated, okay, without experiments. You don't need to necessarily do an experiment to find a number for conversion using the equilibrium route. So this is something that is doable at the beginner's level. So what we do is the next step. Conceptually, one has to proceed that using the principles of equilibrium, okay, what is the maximum conversion that's possible for ethylene and benzene going to ethyl benzene? Is the question make sense? Does the question make sense to all?
Yes, sir.
Yeah.
Yes, sir.
So that means now can you use DWSIM again to answer this question?
Yes, we can use the equilibrium reactor too.
Fantastic. So now all we are going to take is we are again going to take a reactor. Instead of that, now we will change it to an equilibrium reactor. It is ethylene and benzene, and and the product could be anything. I mean, anything in a sense, it is a combination of these may come. But here you need to have something called temperature and pressure, correct? You need to specify this temperature and pressure.
Yes, sir.
Who is going to tell you this temperature and pressure? Literature, okay. Then if you don't have the literature, if you're the first person to build a plant,
Sir, we should know the operating conditions in order
but
to.
how to know? Who is going to tell you that operating condition? So that means who is going to give you this range?
Maybe by
Sir, we have to.
We can do trial and error.
Yeah, and somebody else, trial and error. Then
So using
We
thermodynamics.
can use the,
yeah.
we can use the optimum temperature progression.
But we really do not know, right, what is optimum. As I said, if an already plant is available, then you may have. If already somebody is made available these things, then it is a different case. But it's okay. You just have a DWSIM tool, and you know your fundamentals of chemical engineering. I mean, you know the concept, you have the tool. That's it.
So maybe we can run a sensitivity analysis to check it out.
Yeah. So good. All of you are able to think. So all you have to do is the same. As somebody said, it's very simple. It's a trial and error. Right? I'm not introducing the word sensitivity analysis, though that is what you will see eventually in the subsequent tutorials, because that's the only terminology or the name of that menu. But even without knowing that menu name, what one can do is, can you not change the temperature, right? You take, like, say 25 degrees, then you take 30 degrees, I don't know, you take then 100 degrees or something like that, right? And then try to get what is the conversion. Is this possible using DWSIM?
Yes, sir.
Yes, sir.
So that means now, are you able to understand that? I mean, in a sense, are you feeling empowered that you are now able to generate this window yourself?
Yes.
Right. Now, let me draw this curve. Okay, this curve has a conceptual basis into that, but I'm not going to discuss on the conceptual basis, nor I'm going to tell this is the curve for ethyl benzene production. I'm just trying to draw some curve. Okay, this is just a curve. Let us assume that if you do in DWSIM, you are probably getting points like this as a function of temperature. So you draw a smooth curve like this. This is what you have done in OpenOffice Calc. So you can draw this with these points, and you got this. Let us assume that this is something like 95. This value is something around 95. And let's say that this value is something 80. Some numbers. Understand from this. What do you understand from this? One is, as temperature increases, your conversion is increasing for this graph. Correct? As you increase the temperature, the conversion is also increasing. Correct? And the conversion is always less than 100. Correct? In this case.
Yes.
Yes, sir. Yes.
It is not touching 100, right? It's not 100 is somewhere here. It's
To
not going
take
like
infinity to reach 100, sir.
We do not know because you tested only till this. You only tested till this. So only if I test further, I would know. Otherwise, I will not be able to know that. Correct? But with this information, suppose if I now fine tune your question of, if I need my reactor to operate such that my conversion is at least 80 and above. Okay, so it is at least 80 and above. Can you get me the temperature?
Yes, sir.
Yes.
Simple. Because we will drop, we are very good in the basics of graphs. So we will drop a perpendicular, we will identify this temperature. Let us assume, I'm just putting some fictitious numbers. These are not technically valid numbers. So I'll just put it as, like, say 150 degrees Celsius, suppose here. So this is actually 150 degrees Celsius. Right. So if I put like this, so this means that at any temperature which is greater than 150, your conversion is going to be greater than 80%. Do you agree? Suppose if these numbers are true.
Yes, yes, sir.
So now are you happy that you are now finding the information? Nobody else is giving that, right? You are developing the digital plant. Slowly your digital plant is getting developed. So now at the end of this exercise, you have a reactor, you have an ethylene and benzene. If it is going to be an equilibrium reactor, and if its temperature is anything greater than let's say 150 degrees Celsius, you are very sure that ethyl benzene will be 80% here, at least. And the rest would be obviously unconverted ethylene and benzene, correct? Right.
Yes,
Yes,
sir.
sir.
So that means, now the next question, right? Is ethylene and benzene available at 150? Or how to make the reaction temperature to 150? I'm not saying 150 is the final answer, but this should be the first question, right? So that means we need to, do you think ethylene and benzene will be available somewhere else in a warehouse, that you will have a storage tank here? This is at 150 degrees Celsius, this is at 150 degrees Celsius, ethylene and benzene, and you can directly send here. Do you think it is possible?
No,
We'll
sir.
keep a preheater.
No, sir.
Correct.
No.
Right. So this is not possible. Right?
Yes.
But that means this gives you a concept that you need to put a heat exchanger before your reactor, correct?
Yes, sir.
Yes, sir.
So now can
Yes,
you
sir.
understand the flow sheeting problem that they have given? They have given a sequence, but how was that sequence arrived? That's what I'm making you think. I'm just probing you, right?
Yes,
So
sir.
that means now you will not put a reactor with just ethylene and benzene, but what you will put a heat exchanger, and maybe you will put like this. Correct?
Yes, sir.
And this heat exchanger has to be heated. So that means you will supply energy into this. So I'll use the word small e because I've used ethylene here. Correct? This is the simplest. I'm not saying it is shell and heat tube, heater, nothing. Right? By the way, similarly, can you do this for pressure? We can do for pressure
Yes,
also,
sir.
right?
Yes, yes.
So that means if you master now, or if you get accustomed to DWSIM, can you just generate these kinds of plots? I'm just drawing these plots without explaining, because I don't want to wrap open everything, because then that puzzling to understand will be gone. Okay. Like for example, okay, is it possible for somebody to generate such a kind of curves or the data from DWSIM?
Actually, we are not sure how to do this. I mean, the multiple curves.
Yeah. So that is what you will crack your head and you will come out. So it will not be spoon fed. But if you understand the utility of drawing this curve, then you will find out. How to do is a very different question altogether. The point is, do you want to do this? I mean, do you find a meaning to do this? Right? Because what is the inference from this? What somebody can get, if at all, if they are able to do this? I might have, I'm not saying that this is again a trend that will be there for ethyl benzene or for any other chemical. If suppose I give a curve like this, what do you understand? What is understanding of this curve? Suppose if a curve like this is pressure and this is temperature. So this is in, like say, atmosphere. And this is
Temperature and pressure.
Increase in pressure and temperature leads to 80% conversion, means conversion is increasing, I think so.
No, all these points are at 80% conversion.
At particular temperature and pressure, the conversion will be 80%.
Fantastic. So this is loci of, or the locus of P and T for a given conversion. So that means if you actually use 150 degrees Celsius, probably you have to, let's say, keep 2 bar. But if you use here 170, maybe you have to keep here 2.5 bar. Only then you will get 80% conversion. Otherwise, you will not.
Yes.
Right. Now, again, this is not with respect to ethyl benzene. Okay. This is just an idea I'm trying to pitch into your mindset so that you can use the tool to verify a concept, to learn the concept, and to build the tool from within. So I will take another 5 minutes. Is that okay, Priyam?
Absolutely, sir. No problem at all.
Yeah. So I talked about this part. So the part before the reactor. Now I will go to this part, which is after this reactor. So you got all these three, right? After that, this is only if 80%, and this is like, say, I'm just putting some numbers. Let's say I'll just put equal numbers, 10%, 10%. Do you think you can sell this?
No.
Because
no.
we want 99.9%, we want ethyl benzene. We don't want this much impurity. So that means we need to separate out. And there are other reasons for separating out, because you don't want to waste your reactants just like that, right? But that means we need to now separate. Is it clear? We need to now separate. So that means if you have a stream, so this is your next point, which is your ethyl benzene, ethylene, and benzene. If there is a magical separator like this, which can give ethyl benzene, ethylene, and benzene, you'll be more happy, right?
Yes, sir.
Yes.
Right. But what is the guarantee that this exists?
No.
How this exists?
No.
This does not seem to be viable.
Possible.
Okay, what is the next wish list? Because we always have lots of wish list, right? And the beauty of nature is it does not certainly grants all these things, and that's why we learn chemical engineering, right? If this was possible, then again we don't require excellent chemical engineers, because it just the job simple. The next aspiring thing will be like this, right? Do you agree?
Yes.
This is also nice, right? Because if you get like this, everything of this can go to the reactor. This can go to the reactor. This is going to the product. Oh, fantastic! Very nice separator. Right now, but this is not the only option. Is it clear? So somebody can say, what if it has come like this? So this is ethyl benzene, ethylene, and benzene. Right, a separator. It goes, and you have ethyl benzene and benzene here and ethylene here, and vice versa. You can just mix match a lot of combinations in this. And of course, your fundamentals should tell which of these concepts are possible, not possible. But leaving aside the theoretical aspects of that, do you understand there are lots of combinations such that, and even within a combination, there can be now, different values that you can assign. So that means it can still be like ethyl benzene and ethylene. What if it comes like this? Right. Or what if it comes like, let's say this is ethyl benzene and benzene, ethylene and benzene. Right. Then you need to know, right, how much is there benzene there and benzene here, because it does not matter whether every ethylene you have got, ethyl benzene you have separated. But what if this is still 98% and this is 2%? Still you can't sell it, because this still has to go to another separator. Clear? This still need to go to another separator, maybe a separator 2. If you have ethyl benzene and benzene here, if it is 99.9 and this is like say 0.1, and whatever it is, ethyl benzene and benzene here, this could be probably now 99 and this is 1%, and this is okay. This is our product. So are you able to understand there are lots of combinations that one can have?
Correct, sir. Yeah.
So how to know this combination first of all? And for all these combinations, we need a temperature and pressure, correct? So that means this gives you an idea of we need temperature and pressure for all such separations. And we need to find out which one to use in that, correct? Same like how we discussed for reactor, we need now for a separator. And then comes the choice of equipment, whether it is distillation column or a stripper or an absorber or a fractionator and so on and so forth, correct? I mean, then comes its height, diameter and so on. But the first thing is you need to find this. Clear?
Yes.
So that this again DWSIM helps you, because it's if some of you who have known, who have used Aspen, because I asked the first question yesterday about Aspen, and you all said it's many of you use that and know this product. But can I just tell you, there is one thing that you cannot do readily in Aspen, but you can just do in a flick of a second in DWSIM. You'll be surprised. The DWSIM does that, but Aspen can't do that, right? In Aspen, you cannot find a bubble point or a dew point composition without adding an equipment. Those of you who have used Aspen, can you use Aspen to find the flash or the two-phase composition without adding an equipment? Do you think it is possible?
No,
In DWSIM?
it's possible.
That's all. So don't you think now which is more powerful? You only need to add a material stream, right? And if you just change the temperature and pressure or the other combinations that you have, you might see in the tutorial, you can indeed generate the information that we are talking here. Like for example, again, I'm drawing with temperature, but one can draw with any variable, that what is the percentage of ethyl benzene? Like maybe ethyl benzene in vapor to ethyl benzene total. Or one can define as ethyl benzene in vapor to form maybe ethyl benzene in liquid, and so on and so forth. Okay, this could be anything. We can literally do this. And you know that suppose if this goes to some value and this is what is your favorable zone, that means at any temperatures greater than this, you can achieve this separation. And this point goes for your distillation column. This is your operating point of your distillation column. Are you able to understand? Are you getting the full picture? I just started with ethyl benzene 1000 tons and slowly I'm trying to build my own plant, correct?
Correct, sir.
So I'm having, one thing like Aspen HISIS can do economic evaluation, but DWSIM cannot.
So maybe I would request Priyam, can you support? Because I have never thought on that. Can Priyam help, or is anybody else is there?
Yeah.
And Fossey can add on this.
I can add.
Yeah.
Priyam here.
Yeah. Go ahead, Priyam.
So basically, DWSIM 2 has a economic evaluation sheet. Tool. Okay, but Daniel has made that to be something paid plugin. Now I asked Daniel as to what is the reason behind that as well. So one of the reason that he mentioned is firstly, an economic evaluation tool is something that undergraduate doesn't usually use. That's something that probably is mostly used when the software is used in plant, and probably they can easily afford. Okay, so that is the primary reason. And other than that, yes, the economic evaluation tool is available, and for DWSM as well, with a very nominal price of $27 or $30, I think. So that's a price that you have to pay if you want to buy. So some of the plugins in DWSM are paid just to support his cause, because he is trying to do a lot of things in this and trying to get some developers and all of that. And doing everything as an open source gets very difficult. So the basic thing which needs to be there as an open source and free are still free and open source. But some of the things which are not very crucial to student and not very important to student, some of those plugins are paid.
Okay, thanks.
Okay.
So if Professor Kannan is there, he would immediately make a request that why can't we make a custom defined unit operation or a function which will help to calculate the economics and make it available as part of DWSIP.
Now, what is the cost of Aspen Plus that you tell?
Acha. So should I reveal the answer,
Yes,
sir?
yes.
Or
Yes. Please do that so that we will ask Vaishnavi whether she has ever bought an Aspen Plus copy by herself.
okay. So I have two answers for this. For academic, you will be surprised that it is extraordinarily affordable, probably to greater number of institutes. It is $2,000, which is roughly about 1.2 lakhs per year for 150 user license, which has all the suits of Aspen one can think of in their umbrella, including ICs and so on. This is the academic part. Also, what's a great news. Well, the second part of this information, I can't do any consultancy or commercial activity using this academic license. This academic license is only for teaching. It's just restricted to teaching and pure academic undergraduate work. If I have to do anything with respect to commercial thing, then I need to buy something called tokens. So that means it's like I have a credit card and it is charged topped up with 100 units based on the number of operations or the number of functionalities that I have, the topping will come down. That token amount for the basic package of Aspen 1, which does not include lots of functionality, no heat exchanger, hex, economics, so on and so forth, is per license. That means for one license for 1 year is about 500 crore. One license per year is about 500 crore. Right. So I think no, yeah, Professor Kannan, sir, you can add. Yeah. So this is the kind of cost that is being associated if I have to do any commercial flow sheeting with respect to Aspen. I think it would be eventually same with any other products as well. Is that okay, sir? This Kannan is there.
Yeah, it is about $70,000-$80,000.
Yeah.
What you said, the basic license.
Yeah.
Yeah, that's the cost.
Yeah. Okay. So so I would probably wrap up, and I will not eat into your tutorial time. But all I just want to end the session is try to think of a chemical. Okay. Start with a simple reactor. Okay, if I say reactor, try to make it ethyl benzene, like ethylene and benzene. Now that means here you will have an heat exchanger. So this is what we saw. So that means this is how the reactants come in. Now this needs to go into a separator and probably a series of separators. Okay, and then eventually you will get your product. Correct? I will stop here, and I will expect that you ponder on this, and probably in the Tomorrow's talk, I think in the afternoon, we are going to see the do's and don'ts or the bottleneck issues on what temperature to choose, what is the fundamental of choosing a wrong temperature, and what are the wrong unit operation. So with that open-ended statement, I will stop this lecture. Yeah, Priyam, thank you.
Yeah.
So continue.
Thank you, sir. Thank you very much. Are there any questions on this?
I just want to add, this is what the Aditya Birla Group people have done. They have actually interfaced R with DWSIM and say that you want to do an experiment for a range of values. And then they define it in R, that R will do the statistical thing and say that these are the values at which I need the simulation to be run. And it would automatically fire DWSIM. You can do that because it is open source software and the source code is available. They could do the interfacing and things like that. And they are actually extremely happy. So this is something, very much people would very much want to do.
Okay, here we have. Yeah, Abhishek.
Yeah, so like sir talked about like interfacing, like you have to generate, like let's say you draw a flow sheet, like design a flow sheet using DWSIM, and let's say we have to do using a certain calculation using R as sir said. So what was the interfacing you're talking about? Like how can we get the data from DWSIM and do analysis on R? Like, can you please give an idea about it?
Okay, I don't know the implementation, but it is possible because you have to, DWSIM can be called from command prompt. That means you can do work without GUI in some sense. And so then maybe glue software was written in Python or something. It is done with a lot of software input, but they didn't have to worry about the simulation part because simulation is done by DWSIM, right? They don't have to rewrite that. That's a difficult one. So in other words, because the interfaces are well defined, it is possible to do this kind of a thing. If the interface is not even known, then you can't do that. So that will be the case with proprietary software because they will not reveal how it is coded, how to interface, and things like that.
Okay, sir. Thank you.
Yeah. In other words, even for people who can write such a code, the commercial simulators will not permit because it will not reveal the interfaces, whereas it is a lot easier in an open source software. That is the point.
Okay. Thank you. Thank you very much, sir, for that talk.